So we have already completed the damped vibration and its solution for the over damping, critical damping, and light damping. Okay. So today we start attenuation coefficient. Attenuation coefficient of a vibrating system. Attenuation coefficient of a vibrating system. What is attenuation coefficient? We know that in a damped vibration, what happened? The amplitude of vibration decreases with time. Okay. So attenuation coefficient is that it describes how the attenuation or the amplitude of vibration decreases with time. Okay, it describes how the amplitude of vibration decreases with time. Okay, so there are three types of attenuation coefficient. It describes how quickly the amplitude of a vibrating system decreases over time. This is the definition of attenuation coefficient. In the next paragraph, there are three types of attenuation coefficient. Three types of attenuation coefficient. Number one, logarithmic. Logarithmic decrement. Number two, relaxation time. And number three, quality factor. Okay, so these three are the attenuation coefficient of a vibrating system, which describes how quickly the amplitude of vibration decreases. Now, we will start logarithmic decrement. The ring of logarithmic it measures the rate at which the amplitude of damped oscillatory motion decreases. It measures the rate at which the amplitude of damped oscillatory motion decreases. The next paragraph. So therefore here we write the amplitude of damped oscillatory motion. That means the last case. Okay, light damping. So we know that only for the light damping there is the oscillation. Okay, so we have to take the last solution. Okay, the displacement of the vibrating particle. The displacement of the vibrating particle under damped oscillation is the displacement of the vibrating particle in damped oscillation is mone ache what is the solution, last solution? X equals to c e to the power minus kt sin root over omega 0 square minus k square into t plus 5. Okay, so this is the solution or the displacement of the particle under damped vibration in case of oscillatory motion. Okay. The displacement of the particle under damped vibration is x equals to this one. So which one is the amplitude here? Which term is the amplitude? Which one is the amplitude? C? Only C. E to the power minus kt. Okay. So here the amplitude is A equals to C e to the power minus kt. Okay. A equals to C e to the power minus kt. So you can see that the amplitude decreases exponentially. Okay. Now, what are the successive amplitude of vibration? Therefore, so this is the first amplitude, A1, this is A2, this is A3, this is A4, like that. This is the amplitude and the amplitude increases. So, when we get, in which time we get the first amplitude? What is the time? What is the time at first amplitude? So this is the T time period. Time period of oscillation, one cycle. This is T by 2. So this is that T by 4. So at t by 4 we get the first amplitude. Okay, and after that this one t by 4 it is 3t by 4. Here we get at 3t by 4. That is at 5t by 4, and this is at 7t by 4. Like that. Okay, very good. Let A1, A2, A3, A4, let A1, A2, A3, A4 be the successive amplitudes. Be the successive amplitudes at time t by 4, 3t by 4, 5t by 4, 7t by 4 respectively. At time t by 4, 3t by 4, 5t by 4, 7t by 4 respectively. Therefore, what is the value of A1? A1 equals to C e to the power minus k into t by 4. If we put the value of t here, that is the A1 first amplitude. Then A2 equals to C e to the power minus 3k t by 4. A3 equals to C e to the power minus 5k t by 4. Similarly, A4 equals to C e to the power minus 7k t by 4. So these are the amplitude. Okay, successive amplitude. Now, if you take the ratio of the successive amplitudes, what is the value? Therefore, the ratio of the successive amplitudes. Therefore, the ratio of the successive amplitudes A1 by A2 equals to A2 by A3 equals to A3 by A4 equals to C e to the power minus k t by 4, C e to the power equals to C e to the power minus k t by 4 by C e to the power minus 3k t by 4. Ratio of the successive amplitude A1 by A2, A2 by A3, etc. So C cancel. This is equals to e to the power t minus 1. That is 2. 2k t by 4. Well, 3 का ऊपर चले जाए, इस ऊपर ये क्या होगा? Last 3 होगा तो 3 minus 1, that is 2k t by 4. So this is equals to e to the power k by 2 into t. K t by 2. E to the power k into t by 2. So you can see that this is a constant. देखो, k is a constant. मने अच्छे, k की चीज़ 2 के थोड़ा चिला, 2k is the velocity damping constant. That is the velocity, damping constant per unit velocity, 2k. Okay, so which is a constant? K is a constant. T, time period of oscillation. For oscillation, T is also constant. So you can say this is the D, which is the constant. D equals to T, constant. So you can see that the ratio of the successive amplitudes are constant, which is e to the power k t by 2. Where d is called its decrement. Where the d is called its decrement. The log base e, the log base e, that is ln. Okay, the log base e of this decrement is called, the log base e of this decrement is called logarithmic decrement. Is called logarithmic decrement. Okay, so what is the logarithmic decrement? Therefore, the logarithmic decrement is, therefore the logarithmic decrement is lambda, which is denoted by lambda. Okay, logarithmic decrement is lambda equals to log base e d. So this is equals to log base e to the power k t by 2. What is the value? Kt by 2. Good. Therefore, lambda equals to kt by 2. This is the logarithmic decrement, which is denoted by lambda. So lambda equals to kt by 2. Now I come to the definition. Therefore, logarithmic decrement. Therefore, the logarithmic decrement is defined as the natural logarithm of the ratio of two successive amplitudes. Natural logarithm of the ratio of two successive amplitudes. Of damped oscillation. Of damped oscillation. Okay, so you can see that as the k increases, so lambda proportional to k. So as the damping constant or damping coefficient increases, the lambda also increases. Okay, that means logarithmic decrement increases. That means what happens? The amplitude decreases more rapidly, okay, as the k increases. Now number 2, relaxation time. time or decay constant. Decay constant, relaxation time or decay constant. Definition. Relaxation time of the oscillator. Relaxation time of the oscillator is defined as the time in which amplitude of the oscillator falls off, FALLSOFF, falls off 1 by E or 37%, falls off 1 by E or 37% of the initial amplitude So what is that? We know that the amplitude decreases like this. Amplitude decreases exponentially with time. So according to the definition, what's happened? The time at which the amplitude decreases 1 by E, that is 37% of the initial value. This is the initial value. Somewhere it comes at 37% or 1 by E, and this time is called the tau, relaxation time. The time at which the amplitude falls off 37%. Okay, this time is called the relaxation time or the decay constant. Relaxation time or decay constant. Now we have to find out the value of relaxation time. Look, we know the amplitude of the damped oscillatory motion. We know the amplitude of the damped oscillatory motion is A equals to A0 C e to the power, or A0 e to the power minus KT. Instead of C, we are here A0. Why? Because when T equals to 0, A equals to A0, amplitude, that is this one. As T equals to 0, A equals to A0. Okay, so we write A equals to A0 e to the minus KT. Or A by A0 equals to e to the power minus KT. A by A0 equals to e to the power minus KT. According to the definition, relaxation time A by A0 equals to 1 by E. তাই তো এটা A0 থেকে 1 by E হয়ে যাবে or ফার্স্ট এটা লিখতে পারো A equals to A0 by E. এখন এর ডেফিনিশন A equals to A0 by E, that is A by A0 equals to 1 by E. Well, so this is equals to E to the power minus 1. Equation number 2. So from equation 1 and 2 we get, from equation 1 and 2 we get E to the power minus KT equals to E to the power minus 1. Or now we write here if you have minus K tau, instead of T we write tau. Why? Because now it is equals to this one. Okay, the time at which the amplitude becomes 1 by E, so we write K tau, or K into tau equals to 1, or tau equals to 1 by K. Tau equals to 1 by K. And we know that, although we know that 2k equals to B by n. 2k equals to B by n for the differential equation. Or k equals to B by 2n. Therefore, tau equals to 2n by B. Again, you can see that tau is inversely proportional to 1 by k. That means if k increases, tau decreases. That means as k increases, tau decreases means tau comes here. So time decreases and it becomes like this after time. It is more damped than this one. Because the vibration or the amplitude decreases more rapidly here. So as the k increases, then we can say that the vibration of oscillation is decreases more rapidly. Okay, so this is the relaxation time. Now the quality factor. Number 3, quality factor. It is denoted by capital Q. The ratio of definition. The ratio of maximum value of restoring force to the maximum value of the damping force. The ratio of maximum value of restoring force to the maximum value of damping force is called quality factor. Okay, so therefore quality factor Q equals to maximum value of restoring force by maximum value of damping force. Maximum value of damping force. So what is restoring force? Restoring force is equal. Restoring is proportional to displacement. So what is the maximum restoring force then? When the amplitude is maximum, when the displacement is maximum, then restoring force is maximum, and the maximum displacement is known as amplitude. Okay. Therefore, we know x equals to c e to the power minus kt sin omega t plus 5. Omega equals to root over omega 0 square minus k square. Okay, so we know x equals to this one. Therefore, the amplitude here a equals to c e to the power minus kt. Amplitude a equals to c e to the power minus kt. And the velocity v equals to dx dt. V equals to dx dt. Okay, dx dt. So if you take, it is this is equals to a sin omega t plus 5 like this. Then what happens? dx dt equals to a omega cos omega t plus 5. Okay, a omega cos omega t plus 5. So what is the maximum velocity then? Vmax equals to a omega when cos theta equals to 1, maximum value of cos theta is 1. So when cos omega t plus 5 is 1, then the V is maximum. So therefore, maximum velocity Vmax equals to a into omega. So this is equals to a root over omega 0 square minus k square. Omega equals to this one. Therefore, you know where it is? for small k, this is equals to a into omega 0 for small k. Why? Because we know that when k is less than omega 0, then only we get that solution. Therefore, Q equals to quality factor Q equals to maximum value of restoring force. Here we restoring force is proportional to displacement. That is C into X. So if it is maximum, then C into A. When X equals to A, amplitude. Then that is the restoring force is maximum. And maximum value of damping force. We know that the damping force is B into dx dt. Damping force is proportional to velocity. After that, damping force equals to B into dx dt. Damping force proportional to velocity, that is dx dt. Therefore, damping force equals to B dx dt. First equation. Now it is maximum value of damping force. So it is max. That is V max. So this is equals to C into A by B into A omega naught. Maximum A omega naught. So this is equals to C by B omega naught. C by B omega naught. Okay. Now what is C? We know omega naught equals to over C by M. Or C equals to M omega naught square. And B equals to what? 2k equals to, and 2k equals to B by M. Or B equals to 2k M. So this is equals to C equals to M omega naught square by B hoche 2km omega naught. Second thing M cancel. So this is equals to omega naught by 2k. Therefore Q equals to omega naught by 2k. Omega naught by 2k. Okay, so Q equals to omega naught by 2k. So again you can see that as the k increases, the quality of the vibration decreases. The definition key attenuation coefficient measures how the quality of the vibration decreases or the amplitude of the vibration decreases. Okay, so again you can see that Q is proportional to 1 by 2k. Now what is 1 by 2k? 1 by 2k is again relaxation time. Therefore, Q equals to omega naught into tau, where tau is the relaxation time. Tau equals to 1 by 2k. So again, This is the relation between quality factor and the relaxation time. The last one. This is the relation between quality factor and relaxation time. Okay, so your question may be like this also. Find out the relation between quality factor and the relaxation time. Then you have to find out the quality factor and have to do this one. Okay? Okay. So this is the end of today. The next class we will solve the LCR circuit. That is the analogy between the mechanical and electrical circuit. Okay, analogy between the mechanical. This is the mechanical. Then we have to go for the electrical. If you take a LCR circuit, that behaves like a damped vibrator. Okay.